Hello and welcome to the first video over chapter 18 material. This video will cover halogenation of benzene. The learning objectives are that you be able to predict the monosubstituted product or products formed when benzene is reacted with either molecular bromine or molecular chlorine and a catalyst. And you should be able to draw the structure of the intermediate rhenium ion, as well as its resonance hybrids. After you watch this video, you should go ahead and from the chapter 18 problem set, do parts A and E from number 1 and problem number 2. Okay, let's go ahead and get started. So in this chapter, we're going to learn a bunch of reactions that benzene undergoes. And it's really useful. We're going to break up the reactions into sort of two main chunks. And the first chunk are the electrophilic aromatic substitution reactions. I'm going to go over 5 of these, and you'll be responsible for those on exam number 2. And then after that, we'll sort of draw a line before we start in on the nucleophilic aromatic substitution reactions. That won't be on exam 2. So we're going to focus right now on the electrophilic aromatic substitution reactions. So in this set of reactions, you're going to see benzene acting as a nucleophile. You'll see me abbreviate that NU. Okay. And it's going to be reacting with an electrophile. Here, I'm just giving you an electrophile. Okay. In a substitution style reaction where a hydrogen from the benzene ring is going to be substituted for the electrophile. Okay. And that hydrogen that comes off of the benzene ring will end up part of some inorganic product. So I'm leaving this as just the generic reaction for electrophilic aromatic substitution. We'll see a bunch of different electrophiles since we're going through 5 of these reactions. So sometimes the electrophile already has a plus charge on it. Other times it's generated by using a catalyst. Now for all of these electrophilic aromatic substitution reactions, something that's really important about them is that their intermediates will be positively charged. Okay. So we're going to see that over and over and over again. So let's go ahead and I'm just going to cover the first of these electrophilic aromatic substitution reactions in this video. And that one is halogenation. And then in subsequent videos, you'll see nitration, sulfonation, Friedel-Crafts alkylation, followed by Friedel-Crafts acylation. Okay. All right. So in the halogenation of benzene, you're going to see this done using molecular chlorine or molecular bromine with a catalyst. And that catalyst will be some type of metal salt, either iron 3 bromide or iron 3 chloride or aluminum chloride. Okay, a metal salt is going to act is going to serve as a good Lewis acid, and it's going to help to generate our electrophile. So let's go ahead and I've written out a general reaction here. So we have our benzene here. That's again going to serve as our nucleophile. Okay. And I'm going to go ahead and fill in a hydrogen on here to emphasize that I'm substituting a hydrogen for a bromine. Okay. And let's take a look at how this reaction takes place. So molecular bromine, maybe you're familiar with it being a red-brown liquid. It's pretty easy to use. It's nonpolar, okay? But when we combine this, if we allow a metal salt to be present, such as iron 3 bromide, okay? When these two approach each other, that's going to actually polarize this, so that what we end up seeing is that a pair of electrons here, as this approaches, will form a bond to the iron, and we're going to break this bromine-bromine bond, and this is going to go to this bromine. And so this bromine here is going to form what's called a bromonium ion. It's going to form a very good electrophile. So this here, let me use my red. This is our electrophile. Electrophile. Okay. And then we see here that the metal salt now has a formal minus charge on it. Okay. So in this reaction here, we need our metal salt to catalyze the bromine, in this case, into becoming this bromonium ion, which is going to serve as a really great electrophile. Okay, so just a reminder, we're going to see lots of metal salts here serving as catalysts. They are good Lewis acids. They can accept an electron pair. Okay, so let's go ahead and dive into the mechanism of this reaction. So this mechanism occurs in 2 steps. So so we've already started here. We've already made our bromonium ion, okay? So just a reminder, here's our bromonium ion. In the first step of the mechanism for substituting a hydrogen on the benzene ring for a bromine, the first step is the rate limiting step. And this is where we have remember the benzene ring here is serving as a nucleophile. This is our nucleophile. This is our electrophile. So in the first step of the mechanism, we have nucleophilic attack. Okay? So our benzene ring is the nucleophile. What part of it is nucleophilic? So remember, you have these pi bonds, right, delocalized throughout here. So we're going to take a pair of electrons from a pi bond and attack the bromonium ion. Now, when this happens, we're going to make an intermediate that has temporarily lost its aromaticity. So we have to put in energy for this to happen, okay? This is an uphill step. So I'm going to go ahead and draw what we're going to come to learn are called rhenium ion intermediates. Your textbook also refers to these as sigma complexes. So just a reminder here, if I've got a hydrogen here, I've also got a hydrogen here, right? And in the first step of the mechanism, if I have added, so I'm going to keep this hydrogen here, if I add the bromine, I'm going to put this in red, okay? So notice here, we used the pi bond electrons, okay? So we took that pair of electrons to form a bond to our bromine, not boron. And now this carbon has an octet, but this carbon just has 3 bonds. And so it has a formal +1 charge. So it's a carbocation, but it's a special type of carbocation. This carbocation is on what used to be a benzene ring. And so it has a special name. It's called an rhenium ion, okay? And what your book calls the sigma complex. I tend to refer to it as a rhenium ion for the sole reason that it reminds you that this has to have a charge, okay? So this is resonance stabilized. So we can draw other resonance hybrids. And let's do that. And you need to make sure you can do this. Just a reminder, when you are drawing resonance hybrids, the net charge of what you're starting with doesn't change, okay? So let's say here, I'm going to go ahead, let's use a different color. So since there's a plus charge, I'm going to move a pi bond and move it over here towards the plus charge. This carbon here is sp3 hybridized, so I can't move this pi bond here, okay? But I can do this, and then I will have a double bond here. So now this carbon has an octet. I still have my hydrogen. I still have my bromine here. I still have my double bond here. Now, what am I missing? Right here, a formal +1 charge. Okay, there's just one hydrogen there. No, you don't have to draw in the hydrogens if you don't want to. Remember also when you're drawing resonance structures, you cannot rotate, okay? You cannot move the nuclei, meaning you cannot move the atoms. Okay, so then we can also draw another resonance hybrid here. Let's pick a color. Let's do this. I'm going to move this here. Okay, and then when I do that, just since I drew this in before, I'm just going to be consistent. And I still have this here. Now I've moved this here. And now I have a formal +1 charge on this carbon. It doesn't matter if I put the plus charge inside the ring or directly outside. It's up to you. Just make sure it's clear that it's on this carbon and not this one or this one, okay? And then I can't get the plus charge over here, right? Because I already have 4 bonds on this carbon. So I've got here 3 rhenium ions, okay? And this represents our intermediate, what your textbook will often refer to as the sigma complex, okay? But I'll refer to it as, they also call it an rhenium ion too. All right, so that's in the first step. This is the rate determining step. So the energy of activation for this step is the biggest. Okay, step 2 is where we see deprotonation. So notice here that this is not aromatic, right? This is a not aromatic intermediate because you have lost the full conjugation here of the ring, right? So in the second step, we have to get back to aromaticity. So what we're going to do is we need to restore aromaticity by deprotonating. So what we're going to do is just take our, I'll pick our red here, just so you can see it. I'm going to rip off this proton and then move this pair of electrons here. So I'm going to break this bond to do that, and that, notice I'm regenerating my catalyst. So I'm grabbing this proton, and then I'm going to move this pair of electrons here. Okay, so when I do that, what do I get? Well, I get this. Okay, I've restored aromaticity. I have my inorganic byproduct. This is a gas. Okay. And I tend to get a good yield, around 80% yield. I just write here that the catalyst is regenerated. That's going to be regenerated in the form of FeBr3. So remember that a catalyst is not consumed in the reaction, so that's why I'm not writing it as a product over here. Okay, all right. So let's take a look at the reaction energy diagram for this reaction. And I just want to mention, we can also do this reaction using molecular chlorine. So molecular chlorine is a gas at room temperature. It's extremely toxic, whereas molecular bromine is this red-brown liquid. Is much easier and safer to use. Molecular chlorine that was used in World War I as a chemical weapon So, you know, if you have your choice in the laboratory of which you're going to use, you know, you tend to use what's safer, and that's the molecular bromine. Okay, so I mentioned that this was a two-step mechanism. In the first step, that was the rate determining step. Okay. This is our transition state for that. Here, the intermediate is our rhenium ion, or that sigma complex. And then in the second step, we have deprotonation, and we restore aromaticity. And so you'll notice that here, my product is lower in energy than the reactant. So this halogenation reaction is both exothermic and exergonic. I'm just going to write exergonic here. And I want to point out that the addition reaction, which I'll show that this step here, this turns out to be endergonic, and that makes a lot of sense, knowing what we know about aromaticity. So if I were to ask you which of these products is going to be, you know, lower in energy, I'm just going to put the bromines on like this. So this is the addition product. So notice in the addition product, we end up with a product that is not aromatic. In the substitution product, we end up with a product that is aromatic. Okay, so it makes a lot of sense that this would be an endergonic, right? Endergonic process, whereas this one is exergonic. Okay, so we can do this same reaction using molecular chlorine, and we can use as a catalyst either iron 3 chloride or aluminum chloride. The mechanism is the same. So you should practice this now. Up next will be nitration.